Exercise 1.1, question number 3. Check whether the relation R defined in the set, the given set, we will name it as A, which is 1, 2, 3, 4, 5 and 6. The relation R is given as set of all A comma B such that B equals A plus 1. We have to check whether it is reflexive, symmetric or transitive. We will write the relation in the tabular form or rooster form. If A is 1, B is 1 plus 1, substitute here, B will become 2. If A is 2, B will be 2 plus 1, 3. If A is 3, B becomes 4. If A is 4, B is 5. And if A is 5, B is 6. And if A is 6, B becomes 7. But 7 is not there in the set, so we should not write this element. Now we will check whether it is reflexive or not. 1, 1 doesn't belong to this set R, the relation R. Therefore, we can say that R is not reflexive. Any one counterexample will be enough. Or 2, 2, 3, 3, 4, 4. These are not there in the set. Now let us check whether it is symmetric or not. 1, 2 belongs to R, but 2, 1 doesn't belong to R. Therefore, R is not symmetric. Now the third one, let us check whether it is transitive or not. I am taking 1, 2 and 2, 3. Remember, for transitive relation, you have to take two elements in such a way that this is a common element. A, B, B, C form. Okay, they belong to R, but check for 1, 3. 1, 3 doesn't belong to R. Therefore, we can conclude that R is not transitive. Now question 4. Show that the relation R is defined as R is equal to set of all A comma B. So the relation is defined on the real number set of all real numbers, and the relation R is defined as set of all A comma B such that A is less than or equal to B. We have to show that it is reflexive and transitive but not symmetric. So it is an infinite set. Now if I take A comma A, I can say that it belongs to this relation, as A is less than or equal to A, I can say, because we have equal to sign here. For all real values A belonging to R, it is true. Therefore, I can conclude that R is reflexive. Now let us check whether it is symmetric or not. Not symmetric, we have to prove. So I can give a counterexample. If a condition is not true, we can use examples, counterexamples. But if a condition is true, you have to give a general proof. 1, 3 belongs to R, because 1 is less than or equal to 3. But 3, 1 doesn't belong to R, because 3 is not less than or equal to 1. Therefore, R is not symmetric. Okay, next we have to show that it is transitive. So we have to write the general proof. We cannot use examples to prove that the condition is true. So let us consider two elements A, B, B, C. belonging to R. For a transitive condition, you have to take the element B common. Okay, which implies the condition should be satisfied. So AB belongs to R means A should be less than or equal to B, and BC belongs to R means B should be less than or equal to C, which implies A is less than or equal to C. Therefore, I can say that A, C belongs to R, and it is true for any three real numbers taken from the set R, real number set. Here the real number set is capital bold R. It is denoted by bold letter R, and the relation is the other R. So here this is the real number set R. Okay, therefore I can conclude that the relation R is transitive. Let's do the next question. Question number 5. Check whether the relation R in R defined by the given set is the real number set, which is bold R. This is the real number set. And the relation R is defined as set of all A, B such that A is less than or equal to B cube. We have to check whether it is reflexive, symmetric or transitive. We are going to use the examples which we used for the second question. If you memorize the examples, it will be easy. In the exam, no need to waste time trying for the counter examples. So half, half. It doesn't belong to R because half is not less than or equal to half cube. Half cube is 1 by 8, which is a lesser quantity. Therefore, R is not reflexive. Now for symmetry, we will take 1, 2. 1, 2 belongs to R because 1 is less than or equal to 2 cube. But 2, 1 doesn't belong to R, as 2 is not less than or equal to 1 cube. Therefore, R is not symmetric. Now for transitivity, we will take 9, 4 and 4, 2. These two elements are in R. 9 is less than or equal to 4 cube and 4 is less than or equal to 2 cube. 4 is less than or equal to 8 and 9 is less than or equal to 64. But 9, 2 doesn't belong to R, as 9 is not less than or equal to 2 cube. 2 cube is only 8. Therefore, R is not transitive. So in your textbook, next to the second or fifth question, write down these examples and memorize. So it will be easy for you to write it in the exam. You have so many examples. 9442. This is to show that it is not reflexive. This is to show that it is not symmetric, and this is to show that it is not transitive. Now question number 6. Show that the relation R in the set has 3 elements, 1, 2, 3, given by, the relation is given by 1, 2, 2, 1. Only 2 elements are there in this relation. We know that a relation is, the definition of a relation is a subset of A cross A. A has 3 elements. So 3 3s are, A cross A will have 9 elements. Out of these 9 elements, this relation has 2 elements. So this is a subset of A cross A, this R. We have to show that this relation is symmetric but neither reflexive nor transitive. Okay, I can say that 1, 1 doesn't belong to R, or 2, 2, or 3, 3. Any one counter example will do. 1, 1 doesn't belong to R. Therefore, I conclude that R is not reflexive. Let us do the second one. 1, 2 belongs to R. 2, 1 also belongs to R. Similarly, if you take 2, 1, 1, 2 is there. So we'll write the general proof because it is symmetric. A, B belongs to R implies B, A belongs to R. And it is true for any AB taken from the set 1, 2, 3. Therefore, I can conclude that R is symmetric. Only two elements are there. So if 1, 2 is there, 2, 1 is there. If 2, 1 is in R, 1, 2 is also there in R. Therefore, we conclude that R is symmetric. Now let us check the third one, transitive condition. 1, 2 and 2, 1, they belong to R. But check for A, C, that is 1, 1, doesn't belong to R. Therefore, R is not transitive. Now question number 7. Show that the relation R in the set A of all the books in the library of a college. So the given set A is set of all books in a library of a college. The relation R is defined as set of all x, y such that x and y have same number of pages. We have to show that it is an equivalence relation. Equivalence relation means it should be reflexive, symmetric as well as transitive. Let us check whether it is reflexive or not. So x, x. Definitely x and x will have same number of pages. So I can say that x, x belongs to R as x and x have same number of pages. And it is true for any book taken from that library. Therefore, I conclude that R is reflexive. Okay, the next one. Let us check whether it is symmetric or not. We have to show that it is an equivalence relation. Of course, it has to be symmetric. So, if I take x, y belonging to R, that means x and y have same number of pages. If x and y are having same number of pages, I can say that y and x are having same number of pages. So since these two books are having same number of pages, y, x will be in the relation because the condition is satisfied. And this is true for x, y taken from the library A, set of all books. Therefore, I conclude that R is symmetric. Now let us prove that it is transitive. So for transitive condition, we take two elements x comma y and y comma z. Remember, for transitive condition, we take this as the common element. Okay, let us consider that they belong to the relation R. What does it mean? X and y have same number of pages. Similarly, y and z also have same number of pages. So if x and y are having same number of pages and y and z are also having same number of pages, which implies x and z have same number of pages. Therefore, I can say that x comma z is an element of the relation R, and it is true for the three books A, B, C taken from the set of all books A. Therefore, I conclude that R is a transitive relation. So we have proved that it is reflexive, symmetric as well as transitive. Therefore, I conclude that R is an equivalence relation. That's what we have to prove. Now question 8. Show that the relation R in the set A, so I am writing the given set on which the relation is defined. The relation is defined on the set 1, 2, 3, 4 and 5. And the relation is R is equal to set of all A comma B such that absolute value of A minus B is even. We have to show that it is an equivalence relation. Okay, let us first prove the first part, that it is an equivalence relation. So A comma A, I can say that it belongs to R because absolute value of A minus A is 0 and it is an even number, and it is true for any A taken from the given set A. Therefore, we conclude that R is reflexive. Now let us check whether it is symmetric or not. Let me consider AB belonging to R. So if I take an element from R, definitely the condition has to be satisfied. That is, absolute value of A minus B is even. I can say absolute value of B minus A is also even, because absolute value of A minus B and absolute value of B minus A are same values. Because of absolute value sign, both are positive. Therefore, I can say that B comma A belongs to R. And it is true for the two elements A and B taken from the given set A. Therefore, I conclude that R is symmetric. So this condition is important. You have to write that. If AB belongs to R, we have proved that BA also belongs to R. Now let us check whether it is transitive or not. So for transitive condition, we take two elements AB and BC such that this B element is a common element. If they belong to R, by the definition of the relation, I know that absolute value of A minus B and absolute value of b minus c, both are even. Now I have to add these two numbers, but we know that absolute value of x plus absolute value of y is not absolute value of x plus y. They are not equal. So I will take, since it is an even number, I can take it as 2n, multiple of 2, and absolute value of b minus c as 2n. That is also, so I have to remove the absolute value sign. So to remove the absolute value sign, I have to put plus or minus. Similarly, remove the absolute value sign here, b minus c is equal to plus or minus 2n. Now we can add. So I'm adding these two equations, add the left hand sides. So a minus b plus b minus c is equal to plus or minus 2 times m plus n. Plus or minus 2 is common, so I have taken it as a common factor. Now b gets cancelled, so we get a minus c is equal to plus or minus 2 times m plus n, which is equal to, I can write absolute value sign. So absolute value of a minus c becomes 2 times m plus n. Because I have put absolute value sign, I can remove the plus or minus sign, which implies absolute value of a minus c is even because it is a multiple of 2. So the definition is satisfied. So I can say that a comma c also belongs to R, and it is true for the 3 numbers taken from the given set A. Therefore, I conclude that R is transitive. Now we know that R is reflexive, symmetric as well as transitive. So I conclude that R is an equivalence relation. Now the second part of the question. Show that all the elements of 1, 3, 5 are related to each other and all elements of 2, 4 are related to each other. So if you consider the set 1, 3, 5, all are odd numbers. So we know that difference between two odd numbers is even. See, for example, 5 minus 3, it is 2, which is an even number. So if you take any two odd numbers and subtract, the difference will be an even number. So you can write that the elements of 1, 3, 5 are all related to each other as the difference between, that is the reason which we are writing, difference between any two odd numbers is even. Two odd numbers is even. Therefore, all elements are related to each other. Okay. Similarly, the elements of the set 2, 4 are related to each other. Only two elements are there. 2 is related to 4 and 4 is also related to 2 because the difference is 2. Absolute value of 2 minus 4 or absolute value of 4 minus 2, both are 2, which is an even number. Related to each other as the difference between two even numbers is even. And then one more sentence is given, but no element of 1, 3, 5 is related to any element of 2, 4. So we'll write that also. This is our first one, first answer, second, now the third one. No element of the set 1, 3, 5 is related to any element of the set 2, 4, because the reason is if you take an element from this set and another element from this set, the difference, for example, this is an odd number, this is an even number, the difference will be an odd number. That's why the elements are not related. We can write that reason, because the difference between an odd and even number is odd. That's why the elements are not related. Now, if you see these sets, see the given set is 1, 2, 3, 4 and 5. And we have written two partitions of this set A. This is one partition and the other partition is 2, 4. These are called partitions or equivalence classes also we can say. And this can be denoted as equivalence class of element 1. That means the elements which are all related to 1. 1 is related to 1, 1 is related to 3, 1 is related to 5. And I can denote this as equivalence class of 2. Because 2 is related to 2, 2 is related to 4. An equivalence class of 1, an equivalence class of 3, an equivalence class of 5 are all equal, same. Because 5 is related to 3, 5 is related to 1, 5 is related to 5. Similarly, equivalence class of element 2 and equivalence class of element 4 are same. Okay, let us see the definition of equivalence classes. See page number 4. See page 4. So equivalence classes means for example, if I denote the equivalence classes by AI, the first condition is all elements of AI should be related to each other. Elements of AI are related to each other. Like in this previous example, 1, 3, 5 are related to each other, 2 and 4 are related to each other. So elements of those sets should be related to each other. Then the second condition is no element of AI is related to any element of AJ where I is not equal to J. That is, if you take, for example, let us take this. If you take element from this first set 1, 3, 5, they are not related to the element of the second set 2, 4. Okay, that's what we wrote the answer in the previous question. The third condition is if you join all the partitions, you should get the given set A or X, whatever the symbol is, and then they are disjoint sets. So nothing should be common between them. So these three conditions should be satisfied. If all these three conditions are satisfied, we call those sets as equivalence classes, or we call them as partitions. They are mutually disjoint sets.